Okay, so last time we were discussing interfacial boundary conditions, and we had discussed conservation of mass, and we had finished on discussing conservation of species mass, which is actually probably one of the most complicated ones to deal with, just because the fact that you may have no species mass fraction on one side of the interface and a species mass fraction on the other side. And so the species mass equation, the interfacial boundary conditions usually require the most thought out of all of them. So now we'll do a normal, but we finished those. We discussed all kinds of things, and there's all sorts of assumptions that you can make as to how you're going to model any phase change process, such as evaporation or surface reaction. And even there are different vaporization models, and I only highlighted a few of them that are commonly used in combustion, but there are lots and lots of them. So now we conserve mass and species mass. Now we got to do momentum. And I'm going to break momentum into the normal, which is again pointing up, and the tangential direction separately. And so the conservation law for a particle is the time rate change of momentum in the normal direction is equal to the sum of the normal forces. So here I have a control volume here, and I'm keeping track of all the fluxes of normal momentum going up through the top and in through the bottom. And also we do need to account for the fact that if the interface is moving, we are defining our control volume to basically move with the interface. And remember, we are shrinking the height of this control volume to be nearly zero, basically such that the total cross-sectional area on these sides is negligible. Okay, now for the normal momentum, this takes care of the acceleration. Now we need to take care of the forces. And so the forces are, we have basically pressure, basically pushing on the faces, and we have stress, viscous stress, or some sort of normal stress due to solid mechanics. And then that's defined to be positive in tension. Now there is one other force we need to consider, and that's surface tension. And surface tension exists exactly on the interface and only on the interface. So even though surface tension exists on the sides, it exists only on the interface. So the fact that the interface, or the fact that the area on the sides tends towards zero for our application does not matter. There's still surface tension there. Yes.
Are you scrolling through something? Because we just see the mass generation screen.
The mass generation.
Well, yeah, it says the surface mass generation term needs to be modeled.
That's, you have normal, you have, okay, I'm sharing my screen.
Yeah, so we're not seeing you right on the screen at all either. So it looks like the screen has been frozen from when we started at the species mass equation.
Mm-hmm.
Is it working now?
We haven't seen any movement yet.
Well, shit.
Oh, yeah. Okay. Now it makes sense.
Okay, well, I'm not repeating everything I just said for the past 10 minutes. So normal momentum, conserving forces, and accelerations as normal. The only thing that you probably haven't dealt with in fluid mechanics is the surface tension forces. And so just recall that the sides of the control volume tend towards zero, but surface tension exists only on the surface. So even though the sides are tending towards zero, the surface tension force will still be in there. Okay, and so if you're doing droplet combustion or spray atomization, you do need to consider surface tension forces. They can be very important for some applications. Okay, and so this here would be a normal force due to stress, and this here is normal force due to pressure. Okay, and so with the exception of the surface tension, this looks a lot like the control volumes you guys might have done in your undergraduate fluid mechanics courses. And so we're going to use the general RTT that we derived, and our B parameter is going to be the velocity in the normal direction. And remember that that is defined to be pointing up into the positive fluid. And we can't really accumulate inertia on the surface of the interface. So in other words, then this integral here will tend towards 0. And so then we apply our RTT. We have the net flux of momentum going out minus the net flux of momentum going in is equal to the sum of the pressure forces basically going up. So I have P minus P plus. And so that is, so I'm defining the positive direction going up. Then I got to take care of the stress forces here. And then I have the surface tension forces that are net pulling it down. Basically, they are pulling it down into the curvature. And so I'm not going to derive what that force is. I'm just going to state the result. So you can show that the net surface tension force is given by sigma t, which is the surface tension, multiplied by the divergence of the normal vector. So if I have a curved surface and I define the normal vector as basically pointing out, basically the normal vector will be pointing in all kinds of directions that change with respect to where I am on the surface. Okay, and it turns out, again, I'm not going to prove this, but this divergence of the normal vector, that's a generalized expression for the curvature of the surface. So if you have a sphere, recall that the curvature is just 2 over r for a sphere. Okay, and so basically this is just a really generic way of computing the curvature, because if you have a spray, a liquid jet that's breaking up and it's fuel, it'll look all weird. And so you would need to compute, to account for the surface tension effect, if this is the edge of a water jet, you would need to be able to actually compute the curvature at basically every point on the surface. And so in such a case, you need this very generalized expression here. Okay, and so the net surface tension force, which points down, is just the surface tension times our curvature, and then multiplied by the area of our plane up here. Okay, so then putting it all together, we have our net conservation law, our net inertia balance, our momentum balance, I should say, that accounts for pressure forces, viscous stress, and then also surface tension. Okay, and so you can include all of these effects if you need. A lot of times you don't need to worry about surface tension, but sometimes you do. So I leave it in there for generality. And so I'm just going to go through an example of how we basically work through this equation for conserving momentum across the interface. And we're going to derive something called recoil pressure. So let's just look at our control volume that we used for our conservation of mass example that we did on Friday. So here we just had a vaporizing interface. We have gas on top and liquid on bottom. And we are defining the liquid velocity to be stationary. And we have a vaporizing interface. So the surface of the liquid gas interface is going to be moving down at some regression rate RB. And so we found through conservation of mass what the velocity has to be leaving our, if we know what the density is, we found what the velocity has to be, and it has to be this. Okay, and so we derive this on Friday from conservation of mass, where the normal velocity at the interface is minus RB, and UN minus is 0. Okay, so now if we are going to, so now we're going to find what the pressure difference is across this interface. Okay, and so we just want to see what the normal momentum equation has to say about about a jump in pressure across the interface. And we're going to neglect, for the sake of convenience, we are going to neglect the viscous normal stress, and we're also going to neglect surface tension. But you could certainly include surface tension if you wanted to too. Okay, and so we're going to neglect surface tension. And if we substitute in basically U and I, and UN minus is equal to 0, this term goes away. This term goes away because we are neglecting it. And this term goes away because we are also neglecting it. So we have the change of pressure from the liquid to the gas side will just be equal to this term over here. Oh, okay, and so that's all I did here. So now I'm going to substitute in our result that we got from conservation of mass. And I'm going to substitute that, that expression into here. So this will be substituted into here and into here. And so it sort of explodes into a bit of a mess, but you can keep working with it and sort of simplify it. So here's what it is here. And then I'm going to arrange it. So I move the pressure onto the left-hand side and this over to the right-hand side. This RB here, or basically this RB that's over here, it cancels out with that one over there. So we are only left with a density ratio here. Okay, so we keep working with it. It's just really algebra at this point. And so we can find that the jump in pressure between the liquid and gas side is equal to the liquid density multiplied by this density ratio minus 1 and multiplied by the regression rate squared. And notice that basically this term here is greater than 0, this term here is greater than 0, and this term here is greater than 0. So what this is telling us is that due to phase change, we have higher pressure on the liquid side of the interface than we do on the gas phase side of the interface. So that is due to phase change. On the gas phase side, we will have lower pressure than we do on the liquid phase side. And that has some interesting consequences. But before I do that, I'm going to rearrange this into a slightly different form. So here we can write that the mass flux due to phase change is just the regression rate multiplied by the liquid density. You can use conservation of mass to show that. Okay, and so basically that's just if you wanted to compute the mass flow rate of the vaporizing liquid, it would just be the regression rate multiplied by the liquid density, and then the regression rate is just the mass flux divided by the density. If you work with multi-phase flow and droplets, you'll see this expression used quite a bit, and you'll see it in propellant combustion quite a bit too. Once we start working with it. So now I'm going to take this RB over here, and I'm going to substitute it into there and rearrange. And if I do that, I get this pressure difference here is equal to the vaporization mass flux times this actually specific volume difference. Okay, and now what's very common in this area is we always see here basically quite often there are all these sort of like pressure differences and these specific volume differences. And basically those are called jump conditions. And so these are properties that basically jump in value across the interface. And it's tradition to basically define a jump variable as, here psi is just a generic variable. And if you just see a generic variable by itself in square brackets, it is defined to be a jump condition. And this jump condition is defined to be be the value of the variable on the gas phase side, or the plus side minus the value of the variable on the minus side. Okay, and so the jump in pressure would just be the pressure up here minus the pressure down there. Okay, and don't worry about getting into any scenarios where there'd be confusion with species, with say concentration for a chemical reaction. Basically, these jump conditions and chemical reactions almost never occur in the same line, so there would be no way that you could really get confused. And if you were to encounter a scenario with that, I would use the C notation for concentration. Okay, just to avoid this sort of nomenclature issue here. Okay, so note, we can then use this definition of a jump condition or a jump variable, and we can define the jump in pressure is just P plus minus P minus, and the jump in the specific volume is just 1 over rho plus minus 1 over rho minus. Okay, and so we see here that this term here is just the jump in specific volume across the interface. And this term here is the negative of the jump in pressure across the interface. And so then we can rearrange and we can say that the jump in pressure is just the minus of the jump in specific volume times the vaporization mass flux. And then you can expand them out and put it in terms of a regression rate if you want. These are equivalent expressions. And so this basically means that that if you have any phase change across the interface, there will be a jump in pressure. But if you don't have phase change and you don't have surface tension, there will be no jump in pressure across the interface. And this jump in pressure is sometimes called recoil pressure. And why it's called recoil pressure is you could imagine that you have a hot surface right here. So I'll just shade that red. This could be a very hot frying pan. And on that frying pan, if you put a water droplet, and that water droplet, and you just put it on there cold, for those of you who cook and sort of do this, you'll see if the pan is super hot, this sort of water droplet will kind of dance around and float, where it won't actually touch the surface. It won't actually touch the surface of the pan. So what's actually causing the droplet to float and basically not touch the surface of the pan? Well, as the droplet gets closer and closer to the surface, the droplet vaporizes intensely at the surface here, which of course generates vapor. But if you want to calculate the actual force that is pushing on the droplet, you need to consider the pressure force that's pushing on the bottom of this droplet upwards. And that pressure force is basically coming from the so-called recoil pressure. Okay, and so it's the actual recoil pressure acting on the bottom of a droplet on a hot frying pan is basically what's causing it to float and sort of dance around in funny ways. And because the vaporization is extremely non-uniform, it could be more over here than it is over here. The droplet sort of moves around in sort of weird, random, chaotic ways. Okay, so are there any questions on this so far? Okay, again, these are the kinds of things you just sort of need to get used to them, but momentum is not that much different than what you guys used in your undergrad fluids. It's not that much different. There's just sort of maybe some new nomenclature, and you may have to account for surface tension. Often we don't include that in this class. We probably won't work with surface tension that much, but for the sake of generality, for those of you who will, I just leave them there. Okay, so now we conserve momentum in the normal direction. Now we need to consider momentum in the tangential direction. So by the tangential direction, I just mean the surface out here, basically pointing to the side. Okay, and so we can define a tangential velocity at the surface as just the actual velocity vector minus basically minus the normal component of the velocity vector. Okay, and then our B in the RTT will be the tangential velocity. And so we basically stick that into our conservation law, and we have the time rate change of tangential momentum is equal to the sum of the tangential forces, and I'm going to be defining to the right as the positive direction. So for tangential momentum, which is something you probably didn't account for that much in your fluid mechanics. We have tangential momentum going in through the bottom, and so that's just the mass flux multiplied by the tangential velocity. So it's basically rho. So the tangential inertia going in through the bottom is rho un minus times the tangential velocity, and the net tangential momentum going out through the top is the mass flux rho, basically rho plus un plus multiplied by the tangential velocity at the top. Okay, and so after you guys work with this, you will get used to this. And the free body diagram portion of it is simple. We have the shear forces on the top and bottom. So those are defined to be in the positive direction. And we also have surface tension forces here. And it may seem kind of counterintuitive, like these two surface tension forces here would cancel one another out, but they may not necessarily cancel one another out exactly. And so, for instance, you could have higher temperature over here than you have over here. And in such a case, the surface tension could be lower here than it is over here. And so surface tension in such a scenario is not only going to impart a downwards force, which increases pressure. It is also going to introduce a tangential force on the surface. Okay, and so, and that's usually not very important, but for some special applications, this tangential surface tension force, due to differences in the surface tension on both sides of the control volume, can be important. Okay, but at any rate, and I'll just skip to the result and basically on the lines down here, just state what that tangential surface tension force is. So again, we apply the RTT with B equal to the tangential component of the velocity vector, and that's equal to the sum of the tangential forces. So we have the the shear stress acting on the top minus the shear stress acting on the bottom, plus the net surface tension force. And I'm just going to define that as this minus this. Okay, and so we can show, not even I've never been through this. This has just been handed to me by a surface fluids person. You can show that this net tangential surface tension force is what's called grad S of the surface gradient of the surface tension. And so the surface gradient is a gradient operator that only considers the tangential directions. Okay, and so if we have our surface here and we want to compute the tangential gradient, that is, we do not care about the component normal to the surface. We only care about the component of the gradient that is tangent to the surface. And so that's basically, that's what the surface gradient here is basically, if you actually ever have a need to actually compute it, it is the actual gradient minus, basically minus the normal component of the gradient. Okay, because sometimes if you have a goofy curved interface like this, it may not be too intuitive as to what the tangential gradient is here, because your normal vector is pointing in some weird random direction. Okay, and so in such a case, it's just easier to use this sort of brute force definition. Okay, and so that's just, I just put this here for generality, just so that you've seen it and you're aware that it exists. And this net tangential surface tension force is actually called the Marangoni stress. Okay, and it's caused by surface gradients in the surface tension. And this Marangoni stress, if you are looking, it's important if you're looking at pool fires in low gravity environments like a space station. These Marangoni stresses can cause weird convection cells in a small liquid pool, which can actually cause a combustion wave to actually pulsate and do really interesting, weird transient things. And then basically Marangoni stress is actually what's driving those, is the primary driver of those weird pulsations. And so it can be important for some applications. Most practical applications, it's not important, but it's just something to be aware of, that it exists. Okay, and so we got this general expression here, and we can simplify it and then basically mess with it a bit. Quite often, we know that from viscous flow theory, that in most cases, the jump in tangential velocity should be 0, meaning that the tangential velocity of the gas side of the interface should be the same as the tangential velocity on the liquid side of the interface. And most applications, no slip still holds. And so basically that means that the velocity at the gas, or of the gas and the liquid on both sides of the surface, is one in the same. And so that's all the no slip, that's all the no slip condition means. But there is a caveat to that. If you start violating the continuum approximation, you may not, the no slip condition may not hold. And this can occur if you are concerned with the combustion of nanoparticles, which actually was all the rage here about 10 years ago in research, or very small droplets. And so in such a case, you may actually have a jump, or the no slip condition may not hold, and you may have to apply what's called a partial slip boundary condition. This comes from the kinetic theory of gases. I'm not going to basically go through this. It's just to be aware that if you are resolving an interface of a particle or a gas, and the particle is really, really small, just be aware that the common no slip condition may not hold, and you may have to correct it. And this is one such correction here that I wound up using in my PhD thesis. Okay, and so it's just be aware that basically this exists. And if you want to check whether you need to worry about these effects or not, you need to check the Knudsen number, and that's the ratio of the mean free path of the gas molecules divided by some characteristic length of the surface, and that would normally be a droplet diameter. If this is order 0.1 or higher, then you really need to consider these partial slip boundary conditions. Okay. So then, but if no slip holds, which is most of the time, this sort of nasty looking a tangential momentum conservation equation here across the surface simplifies tremendously. And because if no slip holds, then we can easily argue that the velocity on the plus side is equal to the tangential velocity on the minus side. And I'm just going to call that some basically U tangent. So what that allows me to do is it allows me to factor out the same, it basically means these two parameters here are the same, and I can basically factor them out and then collect these two terms. So I'm going to do that. And if I factor out that tangential velocity and I collect these two terms here, this here is our generalized conservation of mass, which is equal to 0. So this whole term goes bye-bye. We don't need to worry about it. So then basically what's left is this jump here in the shear stress on the surface and the Marangoni stress. And so if no slips holds, we can argue then that the jump in the shear stress is equal to the negative of the Marangoni stress. And so this is why these weird surface tension gradients can actually drive flows, is because on the surface, if you have higher surface tension over here than say you do over here, that means that basically means there's going to be a jump in the shear stress across the surface, and that's actually going to drive a weird flow, either on the gas phase side or the liquid side. And so these effects, they are, again, they're only important for very special applications for combustion, but from a scientific aspect, they are really interesting. But normally, you don't need to worry about the Marangoni stress, and if you do, then this is equal to 0, and this means that if you have no slip and no Marangoni stress, then there's also no jump in shear stress across the interface. And for those of you who've had fluids 1 or fluids 2, you may have actually applied this condition for the classic problem of you have a Couette flow and you have basically 2 layers of fluids. This is fluids 1, and this here is sort of fluid 2. And you have a moving plate, and you wanted to compute the velocity distribution, and you argued that the shear stress had to be the same. Is that the shear stress had to be equal on this side of the interface and as it was on this side of the interface, and by no slip that the velocity had to be the velocity had to be the same too. Okay, and so basically this is just a very formal derivation of that fact that you took for granted that you may have taken for granted in some of your other classes. So are there any questions on this? Okay, so now we go to the energy balance. So we've done normal and tangential momentum. Now we got to do energy, and that one looks the messiest, but it's probably the one you guys are the most familiar. You guys are the most familiar working with, because you dealt with this a lot in thermo, and I need to move these down. You dealt with these a lot in thermo. Oops, one. You dealt. I'll leave well enough alone. You dealt with these in thermo, and you dealt with these in heat transfer. For the Mechis, you have dealt with these in heat transfer. I don't know if you dealt with these crazy control volumes too much in aero, maybe in gas dynamics or comp flow. Okay, so basically for conservation of energy, you don't really need to go through a super formal analysis because you can argue that you also can't really accumulate energy at the surface either. And so that goes away. And so basically conservation of energy just turns into the same steady state version of conservation of energy that you've been using back since your thermo 1 days. It's just now when we do combustion and we have a high speed, high Mach number flow, we have all sorts of surfaces or sources of heat, enthalpy, kinetic energy, and work. So we have work due to viscous stress. We have pressure work, which is part of the, which is part of the enthalpy. We have work due to viscous stress. We have the heat flux, which accounts for heat conduction, species mass diffusion, and that whole big nasty thing that we showed earlier. And also, we may need to account for thermal radiation. And so that's commonly done at this stage by just accounting for a sort of QRAD that is going up from the top. And we're not going to go over how to compute QRAD. It will be a given to you if you ever have a problem that has radiation. You can take an entire class in thermal radiation. Hell, you could probably take 2 or 3 of them. Certainly not here, but just how complicated this gets. But so, but other than basically the hard part about the energy balances is just sort of thinking of all of your sources of energy, heat flux and work. It's very easy to forget 1 or 2 of them, just because there are so many of them, and your control volume starts looking like a porcupine because there's so many arrows pointing out of it. So this here is a very generic one. It accounts for almost everything, at least that I can think of. But yeah, so we apply the energy balance. We have these terms here: the flux of enthalpy going in through the bottom, the heat flux going in, the work due to viscous stress going in through the bottom, the work due to tangential stress going in through the bottom, and the radiation heat flux going in through the bottom. We have work done by the Marangoni stress, and then we have the same net energy term leaving through the top, and we also have work that we need to account for due to basically surface tension if the surface is moving. So in general, there are a whole bunch of terms you need to consider. But again, if you think of a scenario of your choosing, more often than not, you will be neglecting most of these terms. Like for most applications, like for a burning propellant, which is solid, you don't need to consider these 2 terms. You may or may not need to consider radiation, but for simplicity, this is all that is usually neglected. And compared to pressure and the heat fluxes, the basically work due to viscous stress at the surface is also normally very small, and you normally just forget about it. But just be aware that all these extra terms are there, and in some situations you may need to account for all of those effects. Okay, and then also there's the heat flux vector too, and you may need to, and so just remember they need to account for these things too, where this partial t partial n is the partial derivative of temperature in the normal direction. Okay, and so that's all I'm going to do for energy, because the energy equation of all of them is more situation specific than even conservation of mass or species mass. Okay, so you really need to think of your situation and drive it. And then when we start seeing the applications of these jump conditions and things like that, you'll see things, if for a vaporizing gas liquid droplet, you'll see these interfacial boundary conditions being used. Dr. Jackson uses them in his solid propellant combustion code all the time. And so basically all of these sort of interfacial boundary conditions are baked into a whole lot of codes, and your second computer project will basically utilize some of those effects to model a burning propellant using a detailed chemical reaction mechanism. Okay, so are there any questions on the interfacial boundary conditions?
I just have a question about how, and maybe this isn't the right time, you can always answer this when we get to it, but about numerically solving these, because if your mesh is too large, I don't understand how you could actually incorporate this, because then you'd have changes that we've been neglecting because your mesh isn't actually going to zero in the normal direction, I guess.
Well, how this is used in practice is you don't want to resolve all the microphysics on the surface, right? And so what this is, and so let's just say, and we're not going to get into numerics in this class, but I'll just sort of describe briefly how these are used. Is say we have a domain here, I'll call this liquid, and I'll call this here gas. And you don't, and just like you said, you don't want to resolve basically all of those microphysics. So basically, how you use these interfacial boundary conditions is to basically derive a boundary condition at the gas liquid interface that basically connects the two, and all that microphysics that basically you were just talking about is baked into these expressions right here. And so basically you are turning what's going on at the surface into boundary conditions across the interface. Okay?
So that's kind of like how we treat boundary layer flow and connect it with potential flow. Like we resolve the physics within the boundary layer flow and then connect it to potential flow.
Yeah, kind of. Once we get to propellant combustion and we start using these, you will sort of see how they're used. And then it will start to make sense.
Okay, thank you.
Okay. Any other questions? Okay. Thankfully, we have got through the interfacial boundary conditions were not so much of a review, and the real gases was not a review, but the other stuff was. So we are through the super duper theoretical portion of this class, and now we can go to probably what you guys will find more fun, will be some applications. Okay, so the first application we'll be doing, but again, but all of these principles, the reason we spent time on this is that basically all of these principles form the backbone of multi-phase combustion in energetic materials. Is that if you don't have a good understanding of these really fundamentals, it is really hard to get a good grasp on the fundamentals of an explosive detonation or a burning propellant or a burning aluminum particle dust cloud. Okay, and so but now we're going to apply this to some applications. Okay, and so here we're going to go over thermal explosion theory. And the first variant we'll be doing is something called Seminal Theory. Some of you may have heard of that. Some of you may have not heard of that. And so what thermal explosion theory tries to do is you are trying to understand the effect of basically runaway thermally induced chemical reactions. This is important for asking the question. Say I have a chunk of explosive, and that's at temperature T, and it's exposed to some ambient temperature of T infinity. It could be a fire or something like that, basically licking flames on the surface. And the question, and if basically, if this explosive is your next door neighbor, you are probably going to be very concerned about this question here is, can this energetic material suddenly blow up? It's an extremely important question for safety, because energetic materials, because they do carry their own oxidizer, is that you can't just keep the fuel and the oxidizer separate and then they'll be safe. You need to make sure that they don't ever reach a condition where they can basically just where they can react on their own, which means you need to make sure they don't get hot. But you need to, but we want to understand those effects, because on an energetic material, you want to ignite them by choice, not by accident. Okay, so because you don't want the rocket to blow up on the launch pad before you push the ignition button. Okay, and we will be going over two variants of basically thermal explosion theory. One is Seminov, and the other is Frank Kamenetsky. And this is one guy, not two. I don't know why he has a dash in his name like that, but he does. Could be a Polish thing, I don't know. And so these thermal explosions, there are type of explosions called chain branching explosions, and those are discussed in the other combustion class, which is more heavily focused on chemical kinetics and things like that. But what causes, so here we're focused more on thermal explosions. And these are runaway reactions that are induced by temperature. And these are caused by the extreme nonlinearity of the Arrhenius term. Recall that the Arrhenius term is e to the minus EA over RU T. Okay, and so this term is extremely nonlinear. It can act like a switch that turns chemical reactions on or off. So if we were to plot the Arrhenius term for increasing values of the activation energy, we can see that at some conditions it can actually increase by 10 or 16 orders of magnitude if basically if the temperature changes by as little as, say, 400 or 500 Kelvin. So this Arrhenius term acts like a nonlinear switch that can turn the chemical reaction on or off. And so basically what this means is that how fast a chemical reaction proceeds is extremely sensitive to the temperature. So for instance, if we look at, say, this basically this qualitative case here, for example, if we are safe at 300 Kelvin, if we bump up the temperature to, say, 400 Kelvin, we are on this part of this red curve, and now it's going to blow up because we have changed how fast the chemical reaction is going to proceed by many orders of magnitude. Okay, and then this is on a log scale. But if you plot the Arrhenius term on a linear scale, it basically looks like that, is that at extremely low temperatures, like near absolute zero, it's basically zero and flat. Then it starts to curve up. And then this Arrhenius term is bounded by 1, so it cannot get above 1. So at some point, it's going to approach 1 and then essentially become 1 and then stay there. Okay, and so it's this extreme nonlinearity of the Arrhenius term is causing a lot of these issues with, say, thermal explosion, and why these energetic materials are so sensitive to even fairly small changes in the temperature. And so what we'll be doing on Wednesday is deriving a set of, we're going to be deriving Seminal theory for thermal explosions, which results in an ordinary differential equation in the transient form of it, and an algebraic equation that needs to be solved, a fairly easy one, in the steady sense. And then you can apply those to a given energetic material and decide whether it's going to blow up under a condition or not. Okay, and so that's it for the lecture today. Recording.